Right, welcome. So in this series of seminars, we're going to discuss, go through, and gain experience with this topic called conformal field theory. So there's a great many sources you can use to learn about conformal field theory, ranging from the very physical to the very, very mathematical. And the objective of this course is to give you somehow average between a mathematically rigorous presentation and a physically useful presentation of conformal field theory. So we're going to study essentially two references. I'm going to try and flip between two particular references and give you this kind of harmonic mean of the content in a short and hopefully still useful way. Okay, so there's two sources that I like rather a lot, which span the full spectrum from the completely mathematically rigorous discussion through to the completely physically motivated discussion. So the first one is a book by Schottenloher, and it's called A Mathematical Introduction to Conformal Field Theory. This is my personal favorite reference on conformal field theory. He's made great efforts in that, although essentially all the content in the book is mathematically rigorous, he's made considerable efforts to explain the physical connection between the mathematical presentation and the typical presentation of CFT, as you'll find in the second reference, which is a paper of Ginsparg, and that's on the archive. This is a very lovely reference as well. It's this beautifully short and concise summary of the physical presentation of conformal field theory. Wonderfully economical. You get to meet all the important topics in a very short document. But of course, there's some, you have to pay a price, and that is that some of the topics presented here, he doesn't dwell as much on the mathematical rigorous foundations. So these are the two core references for the next coming lectures, seminars. There's of course a third one. It's sort of hard to not talk about the third reference. And I'm just going to write it down as the Yellow Book. If you type into Google Yellow Book and conformal field theory, you will find what I'm talking about. It's an enormous thick book, which is somehow the encyclopedic reference on the topic. This book is, well, great because it's encyclopedic, but it's also very, very long, and it takes a while to build up to actually working with conformal field theory. So those are the references, and with that, we'll start directly by answering the question, why conformal field theory at all? Why should we even learn about this topic? So there's really a bunch of reasons why conformal field theory is an interesting thing to study. I'll mention two that immediately come to my mind. If you have a many particle background, then the main core reason why you should study conformal field theory is that they provide a good, effective description of a system which is at or near criticality, namely at or near a second-order phase transition. That alone should be a reason to study this theory, because these systems are extremely interesting. They exhibit long-range correlations and scale invariance and a variety of other features that make them fascinating and yet very challenging to work with. So having some kind of effective description is extremely useful when trying to understand systems near phase transitions. Now, there's another reason why you should study conformal field theories, and that is because they are, in a sense, the only true quantum field theories. And the sense is that they don't have a cutoff. So they're a cutoff independent theory. Well, they have a soft breaking of scale invariance, but they are quantum field theories without cutoff. So they're like, you know, the quantum field theories that we dream of when we learn quantum field theory. They are somehow fundamental. And in fact, there's kind of a bit more, right? You know, all, well, I'll put quotes around that, are perturbations of CFDs. Now that's something that we learned when we looked at the renormalization group. So CFTs correspond to renormalization group. Fixed points dominate the effective description of systems at or near criticality. I hope that's at least two good reasons why you might want to study conformal field theory. There's a third. Something very attractive about conformal field theories is that by and large you can make it rigorous, mathematically rigorous, the description of conformal fields, at least in 1+1 dimensions. There's all these beautiful, powerful techniques that we have to define and work with conformal field theories, and they can be made, to a large extent, rigorous. And we're sort of converging at the present time on a unification of these mathematical formulations of conformal field theory. And it may be that in our lifetime we're going to see like a general unified mathematical theory of conformally invariant quantum fields. At the moment, that's not the case, but we have three, roughly speaking, competing mathematical formulations of conformal field theory. Whether or not they're all equivalent is a work in progress, but very interesting topic by itself. So that's why you should study it. I think there's two and a bit good reasons why you should be interested in conformal fields. Before we go on, I guess I better say something about the prerequisites for this series. So they're pretty steep. You're going to need to know advanced quantum mechanics, at least many body. You know, if I say Fock space, you're going to need to not be surprised or unhappy at that word. You should also know classical field theory to some extent, although we will review. You should know quantum field theory. There's no point sitting here if you haven't met at least quantum fields in some form. I know you all have. And then a little bit of advanced quantum field theory, at least to the level of path integrals, so you should at least be able to hear the word path integral and know what I'm talking about. So these are the prerequisites. I'm going to assume you know all these things, and I'm not going to pause to review it. I'm just going to go straight into it. The classical field theory, it's probably sufficient if you know Lagrange densities and so on, and Euler-Lagrange equations, but it would help if you knew a little bit of symplectic techniques, so that I could say, you know, symplectic form, and you wouldn't be too shocked. So those are the prerequisites. All right, so there it is, right? You know, we have these main reasons why we should study it. Here's the prerequisites, so let's get on to it. What is it? What is conformal field theory? So I'm going to answer this question slowly through the coming 10 or so lectures. What is conformal field theory? Well, firstly, it's a quantum theory. Although there's no Q here, we typically would say a theory is conformally invariant if it's a quantum field theory. But you know, we should distinguish between whether it's a classical or a quantum field theory. So it's a field theory, either quantum or classical. Invariant or symmetric There we go. That's what conformal field theory is. It's a classical or quantum theory that's invariant or symmetric is another way of saying it. Under a group of symmetries, it's not just any group, it's a special group called the conformal group. There you go. That's the definition. Now, how a theory is invariant under a group of symmetries depends on whether it's classical or quantum. So if it's classical, it just leaves the equations of motion invariant. That's what it means. If it's quantum, however, we have another definition for what it means for a quantum theory to be invariant or symmetric under a group of symmetries. And that's thanks to Wigner's theorem, which I covered in the last lecture of advanced quantum theory. And Wigner's theorem tells us that all symmetries of quantum mechanical systems are realized by unitary or anti-unitary operators up to a phase. So a quantum theory is symmetric under a group G if it yields a what's so-called projective unitary representation of the group G. So it's important to stress that word, projective. That's going to play a really crucial role in our discussion of conformal field theory. And you can see, roughly speaking, how I'm going to structure the course now. So the way I'm going to work is, well, I assume you know about field theory, both quantum and classical. So the main task, the first task of this course is to explain what is this group of symmetries called the conformal group? What is it? So that's the objective for today and the next couple of lectures, to explain what we even mean by the words conformal group. Then we'll look at classically invariant field theories that are invariant under this conformal group, and quantum ones. And the quantum ones will take us on a very interesting detour through the theory of projective unitary representations, and then we will also look at field theory realizations of such symmetries. Yep, question?
What's actually the assumption in Wigner's theorem? So it says that symmetry is implemented as, and then projective unitary representation, but what's the assumption?
So if you have a Hilbert space, that's the input to Wigner's theorem. So what's the assumption that leads to Wigner's theorem? That's the question, isn't it? Yeah. You have a Hilbert space, and now the space of states of a quantum mechanical system with a Hilbert space H is the set of rays in this Hilbert space. And a symmetry is anything that leaves transition amplitudes invariant. And such a symmetry, after working through some sort of equations, has to be either a unitary or an anti-unitary transformation. There's no other way to implement that symmetry operation that leaves transition amplitudes invariant under those assumptions. So that's Wigner's theorem. You can remind yourself of it by looking at the last lecture in this advanced quantum mechanics course online. So let's talk about conformal transformations in d dimensions. Conformal transformations in d dimensions. These are the symmetry operations of a conformal field theory. So I have to tell you what they are, right? You probably have some sense of what they are. You've probably heard words to the effect like their rotations, translations, and scale transformations. We're going to derive all these facts. So the conformal transformations in d dimensions. So we're going to start. We're not going to assume that we live in a 3+1 dimensional universe. In fact, a lot of the beauty of conformal field theory comes from allowing the dimension to change and the index to also change of the metric. So there's a lot of good reasons to leave these things unspecified, or at least arbitrary for the moment. So to that end, we're going to start with a manifold. It's a pretty, I hope, familiar manifold, at least for some values of P and Q. And that's, the manifold is R to the D, where D equals P plus Q, with a metric. So M is our manifold, and it has a metric of, it's not necessarily a Riemannian metric, it could have negative signature. So the metric we're going to assume we have has this form. Our metric is going to look like all ones for the first P entries and all minus ones for the last Q entries. So this class of metrics captures both Riemannian metrics when P is D, Lorentz metrics when P is 1 and Q is D minus 1, and everything else. So that's a fairly general class of manifolds. And there's good reasons to think about manifolds where you may have more than 1 minus 1 here. So there's things to do with the so-called ADS-CFT correspondence, for which it's useful to have, say, 2 minus signs sometimes. Okay, D is P plus Q, yep. All right, and what we're going to do, what is a conformal transformation? Well, it's a change of coordinates at its heart. So, I should say that P and Q are greater than 0 in integers, so P and Q are integers. Right, conformal transformations are smooth changes of coordinates which don't quite leave the metric invariant, not quite, but leave the metric invariant up to an overall scale factor. That's what a conformal transformation is. And as we'll see, this property of leaving the metric invariant up to a scale factor will have something to do with angles, the way we measure angles. So we're going to consider a smooth change of coordinates. X gets mapped to x prime, where x prime is some function of the original coordinates, x. So x are vectors here. Oops. P plus Q. So this is just we're going to choose some coordinate system on this manifold. There is a global coordinate system, we're lucky here. And we're going to consider a change of coordinates. Now that's a prime, and that's the number 1. And, I forgot something here as well. So I write G, but I probably will write eta mu nu. It's very easy to flip between those two notations. If it's not clear from the context, please let me know. So consider a smooth change of coordinates such that the metric in the new coordinate system is an overall scale factor times by the original metric. So the metric under a change of coordinates changes in a particular way. Namely, I think I'll just drop the primes there, make life a little easier. Right? If you describe the metric in a different coordinate system, then the way your original metric will look like in the new coordinate system is according to this transformation rule here. That's the transformation rule for a tensor of type 0, 2. And a conformal transformation is one where the new tensor is proportional to the old one. And here I'm already going to flip notation back to eta mu nu. So that doesn't carry so much information, so I'll rewrite it. Where G prime mu nu so that's what a conformal transformation is. And it's really important that this scale factor omega here is greater than 0. If it's 0, then you have real problems. You have a singularity.
On the right-hand side, there's an x now.
There's an x,
Not an
x,
prime.
x, yeah.
So this is x in terms of x.
X prime in terms of x, yeah.
And the right-hand side is the inverse of
Yeah.
that transformation.
Oh, yeah, if you like, yeah.
Another question.
Yeah.
In the script of David they use the omega squared. I don't know if it's corresponds to the omega is greater than 0, but
Right, okay, yeah, the comment here is that in David Tong's quite fantastic notes on string theory, I have to say, he uses omega squared instead of omega. That, unfortunately, I mean, that deals with the greater than equal to 0 bit, but it doesn't deal with the greater than 0. So, so this is the different notation for the same thing, but you still have to add the condition that omega is strictly greater than 0. Because it's possible for something squared to be 0. So there's one particular property that conformal transformations have that gives them their name. Okay. It doesn't make much difference, but I think it'll make everyone a little bit happier if I do this, right? Yeah. I just realized. So why do we like conformal transformations? Well, they distort your representation of locations on a manifold. But they do so in a way that's kind of controlled. And the way that's kind of controlled is that although distances can get distorted by a conformal transformation, angles never do. So this is the core property that makes conformal transformations rather interesting. So the angle between two tangent vectors is left invariant under a conformal transformation. So if you have two tangent vectors, let's call them u, mu, v, nu, then this angle between them, which is given by this expression, that's left invariant. You can just confirm that by looking at that equation there, that the angle between these two vectors is left invariant under a conformal transformation. Now, you actually are familiar with conformal transformations. You see them all the time when you look in an atlas. So we choose to use conformal transformations to represent the locations of places on the Earth. So we have to distort our representation of the surface of the sphere, but we do so in a conformal way under many projections that you see in your atlas. So we got the definition of something called a conformal transformation. We've mentioned the key properties of this transformation. And now comes the definition of our group of symmetries. It will already be done in the next line. Here is our definition. So the conformal group, the group that we'll be interested in for the rest of this course, denoted conf M, is, well, intuitively it's just the set of all possible conformal transformations. But it turns out that the set of all conformal transformations isn't connected in the same way that the Lorentz group isn't connected, because you can do things like invert one coordinate, x goes to minus x, so that's a disconnected component. So in order just to, this is somehow trivial, disconnected component, so the hard stuff is not those kind of transformations, but rather the transformations that are continuously connected to the identity. And so that's the definition. Is the connected component containing the identity transformation, which is definitely conformal, right? If you do the identity transformation, you can see the metrics left invariant. Scale factor is 1. And it's pretty clear that the set of all conformal transformations forms a group. You compose two, you get another one. The inverse is clearly a conformal transformation. The scale factor just gets flipped. They were by assumption smooth, so you don't have to worry about a smooth inverse. There we go. So this is it. That was pretty quick. Main definition for the course.
Question?
Yep.
If you say connected, with respect to which topology, or what does it mean more intuitively?
Oh, okay. So the question is, what does it mean even connected? Like, to talk about connectivity, we need to have a topology. You can choose extremely stupid topologies where connected doesn't make any sense, right? But the right one is the so-called compact open topology. That's the one you typically use for groups of transformations like this. Connected in the compact open topology. And that's just the one where everything is continuous with respect to entries of the maps. It's the kind of the obvious one where you use the norm to measure, to make balls, open balls. Now, although I've presented this definition just for manifolds that look a bit like Minkowski space and Euclidean space, of course, you can generalize this definition to any manifold that you like with a Riemannian metric or a pseudo-Riemannian metric. The definition down here only needs that you have a metric. It doesn't even have to be Riemannian. And that means for any manifold you can dream up, there exists a conformal group as long as you have such a metric. We will, I guess, look at manifolds. I'm not clear, but maybe in the advanced topics part of this seminar, we'll look at manifolds which aren't just flat Euclidean space or similar ones. And the manifolds I'm thinking of here are Riemann surfaces. You'll be able to look at tori and other manifolds, and there will be a conformal group, a corresponding conformal group for each of those manifolds. We may or may not look at this topic. So there's the group, right? So we have a group of symmetries, and we can go home because isn't it trivial, right? You just look at representations of groups and you just go to some course in the mathematics department and look at the group representation theory of groups, and then they're probably classified, and then isn't that boring? Let's go home. So, but it's not actually. It's surprisingly non-trivial to understand this group. So here's the quantum conformal field theory course. Like, isn't it this simple? Well, it is in some sense this simple. Conformal field theory in quantum mechanics is all about finding unitary representations or projective unitary representations of this group here for various different manifolds. And the really interesting thing about this topic isn't the finding of the representations. They've actually been classified for most of the manifolds we're going to talk about. It's finding them in local quantum theories, and that's where things get really interesting. It's that word local that makes everything very complicated. So essentially, all the unitary representations of the conformal group have been classified and known. You can write down a list of them for various different manifolds. But that's not what makes it hard. Like, all the representations of the Lorentz group are known and classified. That's not what makes relativistic quantum field theory hard. What makes these topics hard is finding these representations in a way that doesn't mess around with locality. There's a tension between knowing the unitary representation of a bunch of symmetries and demanding that that representation is locally implementable. Huge tension between these two topics, locality and unitarity. And that tension is what gives this topic all its richness. So we are kind of done. You know, we could stop here. You could be satisfied that you have a little soundbite version of what is conformal field theory, or we could go down the rabbit hole and see what we find. And we're going to find some pretty tremendously amazing things down there. And the first amazing result is that this conformal group, its very character and nature changes dramatically as you change the space-time dimension. So for large space-time dimensions, for large values of p and q, the conformal group will turn out to be a relatively ordinary Lie group. But as you get to 2 dimensions, there things get extremely interesting indeed. And that's what we're going to look at now as the next part of the course. We're going to understand just what does this group even look like for various different values of p and q. And we're going to do that by using an infinitesimal argument to classify these transformations. You can do this perfectly rigorously, and Schottenloher does indeed do this in his second chapter. Understand these groups for various different values of P's and Q's. However, this infinitesimal argument I'm going to present, this as you can find in the first pages of Ginsparg's paper, is perfectly sufficient and actually corresponds to the local algebra generated by these group of transformations. So it's perfectly sufficient, not entirely rigorous what I'm going to show you, but easy to make rigorous without sort of losing too much. So I'm sort of content with the infinitesimal version. It'll save us quite a few lectures by not going to the full group description. Once you've seen it, however, you'll understand the group description very, very quickly. And the way this argument works is you just consider an infinitesimal conformal transformation. You don't consider a most general one that smears and deforms everything in large scales. Just consider a tiny one that's almost the identity. You almost do nothing. Should be familiar with this style of argumentation from earlier courses on quantum field theory. Instead of talking about the full Lorentz group, we just talk about the generators of the Lorentz group. We talk about Lie algebras instead of Lie groups. This is no exception. We're going to classify the elements of the group in terms of its Lie algebra. And what's an infinitesimal transformation? Well, you take your original coordinate system and then you express things in the new coordinate system, which is related to the old one, just by adding some infinitesimal vector here. So it depends on the position here. It's allowed to depend on x. Now, if we want to call this transformation conformal, there's a condition it has to obey, and that condition is that it leaves the metric invariant up to an overall scale factor like this. So we're going to express this change of the metric in the new coordinate system and say, what does it mean for this metric to be left invariant up to a scale? Don't have any space, so I'll move on. So it'll turn out not any old function epsilon of mu will be allowed, only certain epsilons. Epsilon can't be arbitrarily crazy. Unless the dimension of space-time is 2. How does the metric change? Well, it's a little exercise. The new metric looks like the old metric plus something to order epsilon. And, well, I'll leave it to you to really verify this. I verified it like in a line here. I'll leave it as an exercise, just to test your understanding. So that's how the metric changes under a conformal transformation, which is infinitesimal. You know, here's x prime, ddx prime, expand to order epsilon. I hope you can get a sense of why that's a reasonable equation. We know it's got to be to order epsilon. Now, our original metric, because we're working with flat flat Euclidean space, pseudo-Euclidean space, our old new metric has got to look like our old one, or at least proportional to this diagonal one. And that requires this condition here.
Sorry, what's the letter after the proportional sign? You mean
That's eta.
introduce it?
Yeah. Eta is my synonym here for this metric.
Oh, the sun. Okay.
Yeah. So in order for that to be true, that can only be true if this thing here is proportional to eta. Just take a look at this, right? That's eta, right? G mu nu is eta. And that's eta, or something proportional to eta. It's pretty clear, right? The only thing that you can put there is something proportional to eta, right there. So our condition is that. And you can even work out the proportionality factor pretty quickly. So to actually work out the proportionality factor, just take the trace of both sides, just set mu equal to nu and sum. And you'll see that you get d on the right-hand side and something here. And that should tell you the proportionality factor. So that's so important, we're going to put a box around it. And that implies that our scale factor has a certain formula. It's 1 plus 2 over d, d dot epsilon.
Is this the point at which dimension 2 becomes special?
It's the point at which dimension 2 becomes special. Yeah, you can already smell that something's a bit interesting at dimension 2. There's a 2 there and the dimension there. So maybe... Next step. Now it took me about 10 lines to verify the next equation. I'm never really very efficient at these computations. Maybe you'll find a more elegant way to derive the next equation. What is the next equation? Well, before we get to the next equation, this one's so important I gave it a box. Let's also give it a star. So the next equation, it follows that exercise. Eta mu nu box plus d minus 2, here 2 appears again, d mu d nu d dot epsilon equals 0. D is clearly very special when it's D is 2. Things are very special when D is 2. Yeah, that's a slightly annoying exercise. At least it took me 10 or so lines. It's a consequence of star and the equality of mixed partial derivatives. So you have to go up to third order partial derivatives to prove that equation there. And I don't have an elegant way to do it. laboriously wrote out all mixed third order partial derivatives and eventually arrived at that. Maybe you have a tricky way of doing it. Box, what's box? Just in case you forgot, the D'Alembertchen. Wait on, do I want it upstairs or downstairs? I want it downstairs. Oops. So just if you forgot what box was. Now these two equations here are tremendous. They actually are highly constraining things, star and star star. So I'll leave them up there. So let's just take a look at star star while I'm erasing the board here. You see that there's lots of third order derivatives going on. So that immediately tells you that, well, epsilon had better be at least 3 times differentiable, right? Of course, we've assumed that they're infinitely differentiable, but and in particular, star star, what it tells you is that not only is it 3 times differentiable, epsilon itself actually has to, all third order derivatives have to vanish of epsilon. It's a consequence of star star. There's a lot of equations there. There's d squared equations, and one consequence is this. So let's use star and star star to classify all possible epsilons that could occur. Now we have to break our classification into dimensions because as you can observe, d is 2 is somehow special, right? When d is 2 up there, star star in particular simplifies dramatically. And in fact, it's less constraining, as we'll see. So the first observation is if you put star and star star together, you learn that third order derivatives of epsilon vanish. There's a lot of equations there, you just got to sum them up and subtract them, and then you'll end up concluding that. So that means that epsilon is at most quadratic in the space-time coordinates. It's already kind of interesting. And we're going to classify epsilon by just looking at the orders. So we're going to look at all epsilons which are order 1, which have no dependence on the space-time coordinates. Epsilons that depend linearly on the space-time coordinates, epsilons that depend quadratically on the space-time coordinates. And that'll allow us to classify all infinitesimal conformal transformations. So the first one, A, that's where epsilon is a constant, and in fact, any constant will do. Any constant obeys these equations up here, because a constant gets annihilated by the derivatives here, a constant gets annihilated by that derivative up there, so any constant is in fact a solution. Now, such infinitesimal transformations that have the form of x goes to x plus a constant, we have a name for them. They're called space-time translations. Super. Let's see, what if epsilon is linear in the space-time variables? Then turns out you get 2 kinds of solutions. Either you're forced to write down epsilon has this form with omega antisymmetric, or epsilon has this form, lambda x here.
Antisymmetric you get from plugging it in.
You just get it from plugging it into star and star star. You assume that epsilon is some linear function of the spacetime coordinates. Plug it in, now you've got an omega, or this matrix omega, put it in here, and you take the derivative. You've got omegas here, you take the derivative here. It's this equation which has the bite, and then you already learn that omega is antisymmetric right there. And that equation there offers no new information, because if you first differentiate with respect to x, now you've got a constant, but the constant is just annihilated by that thing on the left. So these conclusions here come from star and not star star. So either epsilon has this form or epsilon has this form for lambda greater than 0. We have names for these transformations. These are called rotations, and these are called scale transformations. Awesome. So already at linear order, we've caught a great variety of possible transformations that we would even identify as conformal. So conformal transformations include Lorentz boosts. So a Lorentz boost is like this. They include translation, space-time translation. So they include the Lorentz group already. Plus, they give you a new type of transformation, the scale transformation. That's not a Lorentz transformation at all, right? A scale transformation changes the metric by a factor lambda squared, or exponential of lambda. So we can see that this group has the Lorentz group as a subgroup, or the Euclidean rotation affine group as a subgroup. All Poincare transformations are in there. And we get something more, scale transformations. Now it turns out that doesn't quite exhaust all the possible conformal transformations that are allowed. There's one special class left. These are the quadratic ones. And they have this form. So the quadratic transformations for an arbitrary d vector b have to look like this. And these are so-called special conformal transformations that involve an inversion through a circle or a sphere. A bit peculiar, but that's what we have. And that's it. That exhausts all the conformal transformations, infinitesimal conformal transformations in space-time dimension d strictly greater than 2. And they're all infinitesimal, so you can build global transformations by exponentiating them or integrating these vector fields. So you just imagine doing one of these little transformations, doing another one, doing another one, doing another one, and so on. And then you should remember that that's gives us, if you repeat such an infinitesimal transformation many, many, many times, that's the same as an exponential of the generator applied to the coordinates. So if you don't remember that, go back to the symplectic geometry course on Lie derivatives and then That should hopefully be a good reminder. And when you do that, you obtain a theorem. I mean, this is not directly how you prove the theorem, but it's certainly, this theorem captures what you get. What you learn is that every conformal transformation that acts on any connected subset of Euclidean space, including, or Minkowski space, including the space itself, right? U can be the whole space itself, has to be a composition of a bunch of different kinds of transformations, which are just the exponentials of these 4 types here. And now I'll write down the exponential form. A translation. The exponential form of an infinitesimal translation is just a translation. An orthogonal transformation. So an orthogonal transformation lambda is just a d by d matrix which leaves the metric invariant. In particular, in Euclidean space, lambda is just an orthogonal matrix, and in Minkowski space, lambda is a Lorentz transformation. And we have 2 more transformations that we can get by exponentiating these generators. There's the dilations. So all conformal transformations are a composition of these 4 kinds of basic conformal transformation. You have to be a bit careful, especially about these special conformal transformations, because it's possible for the denominator to be 0. It's possible to find b's such that that's 0 at some point. And that means it doesn't form a group. It's not even invertible, right? A bit of a problem there. But it's only mildly bad in the sense that these special conformal transformations bring infinity to a finite point, and they take some finite point out to infinity. And so it turns out that if you add infinity in, as you compactify your space-time by allowing infinity to be an extra point, that these compositions of these transformations become a group. I won't talk about that so much, I guess. No, I don't think I will. Just suffice it to say, if you don't add infinity in your, if you don't compactify your manifold, then the conformal group is proportionally smaller. There's fewer transformations that you can have. Conformal infinity is a very fascinating topic in relativity, because in some sense, conformal infinity, the points that want to be there that aren't there, because if you live in a non-compact space-time, the infinities aren't included, those points want to be there. They want to be allowed, because that's where the observables are in general relativity, at conformal infinity. So it's a subtle topic whether or not to include these points. It'll turn out not to play a huge role in conformal field theory. It does play a huge role in the ADS-CFT correspondence and other descriptions of observables in general relativity. I'm afraid we'll be committing far greater sins before the end of this course when it comes to infinities and so on. Now, life is a lot different when D is 2. A lot different. Turns out things don't really matter. The signature doesn't really play a huge role when we talk about the infinitesimal conformal transformations, but when we talk about the global ones, it'll turn out to play some role. D is greater than 2. And here we go. So when the metric's diagonal and positive, so a Riemannian Euclidean metric, this equation star that I wrote down becomes very, very interesting. It becomes the Cauchy-Riemann equations. So if you just write out all the equations star, which I have erased now, but you've got in your notes, then you'll see that you get two equations for epsilon, and they have this form. d1 epsilon 1 d equals d2 epsilon 2, and d1 epsilon 2 equals minus d2 epsilon 1. So it's really crying out for us to recognize that there's a kind of real and imaginary part going on. Right? Because whenever you see Cauchy-Riemann equations, that says that the underlying function is analytic, complex differentiable, and it wants us to write, it wants us to say that E2 is like the imaginary part of some complex function, and E1 is the real part of some complex function. So let's not ignore this hint, and we're going to introduce some complex coordinates to hopefully see that a bit clearer. So you take the first component, that's like the real part, and then you add on second part with an I, it's like the imaginary part, right? And that would be consistent with this Cauchy-Riemann equation interpretation. And of course, whenever you have Z like that, you can introduce the complex conjugate. And then, using this change of coordinates, we can write out the Cauchy-Riemann equations in the form that's a little bit more familiar. Oops. No, epsilon minus I epsilon 2. So this is just, if you like, a change of coordinates. We've done absolutely nothing so far, but this hopefully makes manifest the hint that the Cauchy-Riemann equations is giving us. So, if you remember the first and most important theorem in complex analysis, a function is analytic, it's complex differentiable if and only if it satisfies the Cauchy-Riemann equations. Then that should give you a sense of what an infinitesimal conformal transformation looks like in 1 plus 1 or 2, in 2 dimensions. Namely, it looks like an infinitesimal analytic function. And that is pretty amazing because there's lots of analytic functions. There aren't just quadratic ones. There's all manner of functions can be analytic. I won't talk about those just yet. We'll first talk about global ones, or ones that exponentiate to nice invertible transformations. So a global conformal transformation in 2 dimensions corresponds to an entire holomorphic function. It's a differentiable function with no singularities. And it's got to be invertible for it to be a global transformation. So that's what they look like. Global conformal transformations look like these functions here. And now we see that although there was a hint, a promise that this set of symmetries was really big, it's actually really tiny because of that rather annoying or interesting or fascinating fact in complex variable theory that if you have a transformation, if you have a analytic function that's entire, there's not many opportunities. In fact, it can only be a linear function, especially if its inverse is entire. The only such transformations have this form here. a bit strange. Here I just said there's a wealth of solutions, very many solutions. Infinitesimally, you can take epsilon as cos of x, you can take epsilon as the exponential of x, you can take epsilon as the Riemann zeta function, you can take any analytic function that you like. But if you demand that it's a global transformation, that it doesn't have singularities anywhere, so that it can form a group, all of a sudden you're back down to some extremely boring transformations, namely rotations and translations. Yep.
You expect there to be the group to be bigger than in the d greater than 2 case because there are less constraints, right?
You expect the question is, do you expect the group to be bigger in the d equals 2 case because there's less constraints? The answer is yes, we expect the group to be bigger. But somehow it's not. As a group, it's not bigger. But, and this is the key point, there are so many transformations here that are allowed, locally allowed, but not globally, that are crying out to be symmetries, but which can't be exponentiated. So this is the key point. What we're going to look at is not, and this is the transition from global to local in conformal field theory. We're going to distinguish between two types of theory. We're going to distinguish between globally conformally invariant theories. They're the ones that are invariant just under these perfectly ordinary Lorentz group type transformations, and locally invariant conformal field theories. And it will turn out that the globally invariant ones are richer because there's fewer constraints, they're symmetric under fewer things, than the locally conformally invariant theories, which are invariant under a much bigger class of symmetries. So the more symmetries your theory has, the fewer degrees of freedom it has, and vice versa. So actually, a theory that's invariant under local conformal transformations like this is actually highly constrained, and that's why we like them. Yeah?
Can you say more specifically what you mean by local and global, actually?
We will as the course goes on. In fact, I don't think I can today, in fact, clarify what I mean by local or global just yet. I will get to the topic of what is local or global by the next lecture. All right, I'll say one more thing, and then we'll talk about, that's a good point actually to stop. We'll talk about local symmetries in the next lecture, not in this lecture. So we'll end with like a slight generalization, which will give us a slightly bigger group, very interesting one, but not what you typically see in a conformal field theory textbook as the conformal group. All right, the last topic. If we take R2 and compactify it. So here's what we've done so far. We've looked at R2, common naught. We've just interpreted it as the complex numbers, right? Just by calling y the imaginary part and x the real part. And then we looked at conformal group of C and found out that it was extremely very boring, namely just the linear functions here. But if we compactify C, if we add in the point infinity, then our group can just get slightly larger. A very interesting group we get indeed.
One question.
Yep.
In the beginning, when you defined the conformal transformations,
yes.
You excluded the case that the P or Q can be zero.
Oh, did I? I'm sorry. That was a mistake.
Element Z plus.
No, Z plus is including 0.
Okay, so they do. So then we have to check the case that D is 1.
That's correct. We'll do D as 1 in the next lecture. Sorry, but the question was, didn't I exclude P and Q being 1? I didn't. I said P is an element of Z plus. Well, I didn't tell you what Z plus was, so that was my fault. That's, in my notation, that's the natural numbers union 0. All right, so if we take C, which is just R2, right, just another way of looking at R2, look at its conformal group, then, well, okay, we end up with linear functions. Super boring. Mind you, there's rotations in there, right? Alpha can be complex. There's rotations and transformations and scale transformations in there. So it's not so boring. It's just not a very big group. But if you add in infinity, you compactify. And the way to do that is with this Riemann sphere construction. Hope you remember. If you take the complex plane, draw a sphere, have a point like an observer on the top of the sphere, and the change of coordinates is every point in the complex plane has a corresponding point on the sphere given by the intersection of the line joining this point Z and the point W on the surface of the sphere and the top of the sphere. So the Riemann sphere is a compactification of the complex numbers. It's just like taking the complex numbers and adding in one extra point at infinity. So if you consider this new, bigger, improved manifold, then the conformal group of C union infinity is that of the group of analytic functions of the Riemann sphere to itself, and it's slightly bigger. And I'll give you what that group is. You get this group here, the so-called group of Möbius transformations. You can check that it forms a group, compose two transformations, and you get another one. You find its inverse. Oh yeah, I didn't say the inverse condition. Well, okay. For things to be invertible, you need that the determinant is zero, is not zero of these entries here. So it's a slightly bigger group. This is a slightly bigger group of transformations that you could call conformal transformations when you include the point infinity in your description of space-time. And these transformations can, for example, bring the point infinity to a finite point in the complex plane. And vice versa. You can, with one of these transformations, take a specified point in the complex plane and map it to infinity. And that slightly enlarges the group of symmetries we're allowing, or what we're calling conformal. All right, but that's, I think, where we're going to stop for now. The summary is, what's conformal field theory? It's a local quantum theory that's invariant under this group called the conformal group. What is this conformal group? Well, it's a set of changes of coordinates which leave the metric invariant up to a scale. And in different space-time dimensions, that group looks different. The global conformal group in space dimension bigger than 2 is comprised of translations, rotations, scale transformations, and special conformal transformations. Even in D is 2, it's comprised of exactly the same transformations as long as you add infinity in. But the interesting observation that we made, and we're going to follow up on, is that if we allow our transformations to include singular transformations, so analytic functions that when you exponentiate them, they have poles or zeros, then you have a gigantic group of symmetries. But then we have to answer the question, what does it mean for a quantum system to be invariant under these infinitesimal symmetries? And that's going to be the task, more or less, for the rest of this course. Okay, but for now, thank you very much.